Whenever we have charges, charges are going to interact through what we call the electromagnetic force. Now, the electromagnetic force, we call it electromagnetic because it is the same kind of force that governs interactions between charges or charges and magnetic fields or between magnetic fields. And we'll talk of more variations of this force as we progress in talking about electricity. Now, the electromagnetic force is one of the basic interactions in nature. Another one that you are familiar with is the gravitational force. The other two are the strong nuclear force and the weak nuclear force. Both the strong nuclear force and the weak nuclear force are limited in range. They are focused on forces that govern the nucleus of an atom, or how to hold together the nucleus in an atom. Now, one of the main features about the electromagnetic force, we know that like charges repel. This is different from gravity, where like masses attract, and then opposite charges attract to each other. In the case of gravity, all masses attract. So we don't have the repulsive and attractive force like we have for electromagnetic forces. The magnitude of the force, the electromagnetic force between any two charges, if I have two charges like this charge here, Q1 and Q2, separated by a distance r, the magnitude of the force is given by this expression, K Q1 Q2 over r squared. Now, if you notice, this looks very familiar. This should look very familiar to you. It should remind you of the gravitational force, the universal gravitational force, where you had the gravitational force being equal to G m1 m2 over r squared. Now, r is the separation between the masses here, like it is between the charges here. m1 and m2 are masses, but here instead we have charges. And we have a different constant other than g, the 6.67 10 to the minus 11 newtons meter squared per kilogram squared. We have another constant we call k. The constant k is much larger than g, is 9 10 to the 9 Newton meter squared per Coulomb squared. Now, this expression is what we call Coulomb's law. He's the one who developed it first. So it is the law that governs the interaction between any two charges. When we use Coulomb for the charge, m meters for the separation, then we get newtons for the force. Now, notice here I wrote the equation in terms of magnitude. The direction, you have to evaluate it separately, knowing that opposite charges attract and like charges repel. Let's take this example here. What we have is a hydrogen atom, which is made up of a proton and an electron. They are separated by a distance about this much, 10 to the minus 10 meters. And we know the charges, both of them have a charge equal to the quantum of charge, 1.6 10 to the minus 19. So now if we calculate the magnitude of that force, so that's going to be 9 10 to the 9 Newton meter squared per Coulomb squared times 1.6 10 to the minus 19 Coulomb squared. I'm not worried about the minus sign because I'm calculating the absolute value, which is here, should be the absolute value as well. It seems the image is protruding here, not allowing me to write over it. Where it's allowing me here, I don't know what's going on. Okay, it works now. So 1.6 10 to the minus 19 squared over the separation squared, which is 1.1 10 to the minus 10 meters squared. Okay, now what does that give me? I'm going to calculate it separately here. We have 10 to the 9, and then we have 10 to the minus 19 squared and 10 to the minus 10 squared. Okay. So that's going to be 10 to the minus 19 squared is 10 to the minus 38 over 10 to the minus 20. That gives us 10 to the minus 18 times 10 to the 9. That gives us 10 to the minus 9. So we have 9, 10 to the minus 9. Okay, just calculate again to make sure. Minus 19 squared, that's minus 38, over minus 10 squared, which means over minus 20. So minus 38 over minus 20, that leaves us with minus 18. And then minus 18 times 10 to the 9, that gives us 10 to the minus 9. So we are left with the 9, 10 to the minus 9 times 1.6 squared newtons. And that should give us 9 times 1.6 squared. So that will give us 23 10 to the minus 9 newtons. It's a small force, but it is much larger than the gravitational force between both charges. If we calculate the gravitational force between both charges, the mass of the proton is 1.67 10 to the minus 27 kilograms, and the mass of the electron is 9.1 10 to the minus 31 kilograms. Just notice in here we have 10 to the minus 27 and 10 to the minus 31. That gets us an exponent that's quite bigger here, and then we have a smaller constant for G, so we'll end up having a force much smaller than that. Okay, now just to dot the I's about the direction, you need to remember that like charges are going to repel, unlike charges are going to attract. For example, here I have two positive charges, they repel. So if I'm trying to find the force acting on the force here on the right, that's the direction of the force. Now if I'm trying to find the force acting on the left, that's the direction of the force. Now if notice here, if they repel, it does not matter if they are positive or negative, the direction of the force is still the same. Now, a few things to finalize about this. The electrostatic force, or Coulomb's law, it tells us that the force is proportional to the product of the charges and inversely proportional to the separation of the charges. It is very much like the universal law of gravitation, where the other one is G m1 m2 over r squared. Now, we didn't calculate it, but the electrical force, I alluded to it, is about, but didn't calculate it, it's about 10 to the 40 times stronger than the gravitational force. So an electron and a proton attract each other with a much weaker force gravitationally than electrically. It might be interesting to notice that a finger spark involves the exchange of trillions of electrons, or about 10 to the minus 7 Coulomb.